Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, welcome to SIC1004. It's been a long time since we did this, and I hope that everyone is keeping well and staying safe. I sincerely hope that these emoticons do not apply to any one of you, and I hope that everyone is really being safe, staying safe with your loved ones, and keeping yourself clean, washing your hands all the time. All right, as usual, this is your attendance. Please scan them. And this is actually the attendance for March 9th. So I'm going to take attendance according to the official attendance date. And when you key in your matrix number, please use your old matrix number. All right? Right. Even Yoda studies thermodynamics. Yeah, that's the that's the inspiration. Anyways, I know it's been a long time, but it's good to recap what we have done before. In the first law of thermodynamics, we talk about the initial and the internal energy being equivalent to the heat and work, and the signage of work and the heat and work depends on whether the heat is absorbed or lost by the system, or work is done on or by the system. We also talked about state functions, which are the values that depend on the state of the substance and how the state was reached. Work is the essence of this thermodynamics. First, we talked about work as in physics, which is the opposing force times the distance. But this opposing force for thermodynamics here is actually the pressure, and then you have here the difference in the volume. Two processes were discussed, isobaric and isochoric, and the corresponding PV diagrams are seen here. So the further recapping was actually on how you define the increment in internal energy or the decrement in the internal energy depends on the whether the heat is being released or system does on the work or surroundings do the work or absorbs heat. All right, so the system absorbs heat from the surroundings. Now, this is not entirely new to all of you. The Le Chatelier's principle, when it describes the reversible change, in which even a small modification in a variable will actually cause a reverse reaction. And an example of this is when you have the change in external pressure will lead to the reverse change in the volume and vice versa. All right, so this is actually the expansion of the previous slide. Let's look at an example on how you actually apply the PVW is equal to minus P delta V equation. So suppose you have a gas being produced when a certain amount of iron reacts with HCl. Okay, what is the work done in a closed container and in an open container at a certain temperature? So the first thing that you need to do is actually write down what is the reaction. And so the reaction in this case is what happens when iron reacts with HCl, which gives you iron chloride plus hydrogen. In other words, this reaction produces 1 mole of hydrogen when 1 mole of iron is being consumed. All right. So in a closed container where delta V is equals to 0, that means that work is equal to 0. There's no work done. In an open beaker where the gas is expanded against the atmospheric pressure. So in this case, we can assume that the VF is much larger than VI. all right? And using PV is equals to nRT, and you write that as V as the subject. So we have work is equal to minus P delta V, and we write that V into this equation. So you have work is equal to minus nRT, so plug in 1 mole, the gas constant, and the temperature in Kelvin, so you get almost 2000 joules. Now, in the first lecture, I talk about how thermodynamics is important because thermodynamics allows chemists to actually predict whether a reaction is spontaneous or not. And why that is important is because when you know that a certain reaction is spontaneous, so investing in that project, in that experiment, in that reaction, will be it will be it's something that you can sort of like, it's not costly, rather than if it's not spontaneous and you still want to invest in the project in direction, it may be costly. So when you can predict the reaction to be spontaneous, that really helps. Now, spontaneous processes are those that can actually proceed without any outside intervention. It happens almost naturally. Like if you look at the following diagram, so if you actually open the tab of this vessel, the gas in B will spontaneously diffuse into vessel A. But for the reaction to go in the reverse direction, that's not spontaneous. So the second example of a spontaneous reaction is when you have a nail, a shiny nail, a new nail that spontaneously will become rusty. But for this rusty iron to actually go back to its shiny condition, that's not spontaneous. At a temperature above 0, it is spontaneous for ice to melt, but water will not spontaneously solidify to ice, so it's not spontaneous. So in other words, an irreversible process cannot return the system and the surroundings to the original conditions when the process is reversed. All spontaneous processes are irreversible. Now let's talk about a third process, an isothermal process, in which the temperature is maintained at a constant value by putting the system in contact with a constant temperature reservoir. Now, the thermodynamic definition of reservoir is something large enough so that heat can be transferred in and out without changing the temperature. Now here, the PV diagram for the isothermal process is of a hyperbola. It's hyperbolic. And so to find the work underneath the plot, you have to do an integration of this PV, right? So work is equals to the integration of P delta V. And so you can actually, since P is equals to nRT over V, so nRT you can take out of the integration because those are actually constant. And the integration of 1 over V gives you ln VF minus ln VI. And you can simplify that to be ln VF over VI. So ultimately, what you get is W is equals to minus nRT ln VF over VI. Now, before we talk about the adiabatic change, all right, so adiabatic process, as you know, there's no heat added or removed from a system. So that means that delta U will give you just W since Q is equals to 0. Now, well, here for a monoatomic ideal gas, the total kinetic energy is given by 3/2 nRT. Why 3/2? Now, the extension of this you will learn in year 2 and year 3 when you talk about the partition function, the equipartition. Okay, so you know that kinetic energy as it moves through space, if you consider it moving in space, you have to consider the dimension, the x, y, z dimension, okay, the constituents. So you have the x, y, and z components, and each of this is the half mv square is broken down to half mv x square, half mv y square, and half mv z square. All right. And the equipartition theorem states that for a collection of particles at thermal equilibrium at a temperature T, so this contribution equals that to half kT, in which K is actually the Boltzmann equation. So having said that, it gives you 3 half kT. And if you're talking about in terms of mole, you have 3 half nRT. So therefore, you have delta U is equals to 3 half nR delta T. Now, adiabatic process also produces a hyperbolic graph just like the isothermal process, except that it's much steeper. All right. Now, the next thing that I want to talk about is on the heat capacity. Now, the heat capacity, okay, describe how much heat is actually required to raise the temperature of 1 gram of an object by 1 degrees. And so that's defined by the heat over the mass times the difference in temperature. And each substance has its own specific heat capacity. Let's take an example on how you actually apply that equation. If you have 25 grams of aluminum cooling from 310 degrees to 37 degrees, how much joules of heat are being lost? So Q is equals to MC delta T. So you have 25 grams times that of the heat capacity times that of the difference, and that gives you a negative 6120 joules. That negative signifies that it is transferred out of the aluminum. So if you talk about an ideal gas and written in terms of moles, so use a capital C. Right. When you talk about heat capacity, there are 2 different conditions in which that heat capacity can be defined, whether it's actually at constant pressure, Cp, or whether the heat capacity is at constant volume. Now, the difference between Cp and Cv is that Cp will always be larger than Cv. Now you have to look at 2 things here. First, at the corresponding PV diagrams for the isobaric and the isochoric processes. Now looking at this isobaric process, so you have the work done here, right? But at isochoric process, you do not have any work done. Now, let's remember that in terms of the first law of thermodynamics, the equation delta U is equals to Q plus W. So the delta U here will be delta U is equals to Q plus W. And here, delta U will just be equals to Q. So having said that, at constant pressure, not all of the heat goes into changing the temperature. So you have some work done. But at constant volume, since there's no work done, all the heat will actually goes into changing the temperature, meaning that it takes less heat to produce a temperature change at constant volume than it does at constant pressure. And so CV will always be less than CP. Now, I don't expect you to digest this immediately. So, and I do not want you to memorize this word by word. I want you to understand the concept. And to understand this, you have to put together what is written here and these 2 PV diagrams, and also the first law of thermodynamics, the equation for the isobaric process and the isochoric process. Put them together, and you're able to relate that and digest that better. And if you're mathematically inclined, maybe this will further help in finding the relationship between CP and CV, or at the same time, what's the difference? So here you have delta U is equals to Q plus W, and at constant pressure using the P here to signify the constant pressure. So delta U is equals to Q plus W. And if you rewrite that, Q is equals to delta U minus W. And W work is equals to minus P delta V. So it's a plus here because you have the double minus there. We also have learned that delta U is equals to 3/2 nRT. And the gas law states that PV is equals to nRT, hence P delta V is equals to nR delta T. So putting all this together, these two equations in this, you have QP is equals to 3/2 nRT plus nR delta T. That gives you 5/2 nR delta T. And from the heat capacity equation, so you can equate that and further equals to 5/2 nR delta T, and simplify that gives you Cp is equals to 5/2 R. Now let's do that for constant volume. Work is equals to minus P delta V is equals to 0. Work is 0. And delta U will give you 3/2 nR delta T. And we write that, simplify that, you get CV is equals to 3/2 R. So mathematically, this proves that CV is lesser than CP. So you can put that together, combine that together with the previous slide. All right, so the ratio of this is of the specific heat, which is gamma, is given as 5/3. Cp over Cv gives you 5/3. All right, so that's about all that we're going to cover for this slide. And meanwhile, let's pause and stay clean. So go wash your hands, and we're going to move over to the next lesson. All right, take care, and I'll see you again.